Welcome to today's webinar. We are going to be discussing how to use the fatigue damage spectrum and a few other analysis tools in ObserveView to improve HALT and HASS testing and validation. To start, talk about vibration research's core focus and core values. Our core focus is to make the world's most innovative sound and vibration technology tools, enabling our customers to make reliable decisions and trustworthy products. Our core values are collaboration, capable and competent, accountable and responsible, strong and driven work ethic, do the right thing, and innovation. And this presentation today really is about a few different of these items. One could be innovation, since we really are trying to improve a method that is widely used yet somewhat flawed today. The other part goes back to that core focus statement, enabling our customers to make reliable decisions and trustworthy products. The tools that I will discuss today really are about exactly that, trying to shed more light on HALT testing, what is happening on that table, what that product is being exposed to, and clarifying and helping make engineering decisions with better data and better analysis. So first we look at our history of innovation. We have a history of field data replication in 1995, then Cartosian, fatigue damage spectrum, implemented into software, instant degrees of freedom, and sign tracking analysis and generation. All these tools are really about better understanding an environment and better replicating an environment in a test scenario. So that's been the goal of vibration research since our foundation, really trying to improve and make testing more realistic, all while making things easier to understand and simplifying the engineering process. For our product line, we have two different software lines, VibrationView, which is our control software, and ObserveView, which is our analysis software. And then we have accompanying hardware that works on any of the software, the Observer 1000, the VR9500, and our VR10500. And then we do sell small shakers as a complete product, so that if someone needs a small system, we can provide everything that you need. So let's jump into today's actual content. First, just a brief introduction to HALT and HASS. HALT is really about determining failure modes, whether it be the operating failure modes or destruction failure modes. And what we do is combine a variety of stresses. Typically, the primary stresses, or stresses that are in almost every HALT test, are going to be temperature and then rapid change temperature from heat to cold, as well as vibration. But there is a variety of other stimuli that could be added in conjunction with these. And the goal in the end is to find those operating and destruct limits of the product. One of the goals for today's presentation will be to try to minimize, as you can see in the upper destruct limit and upper operating limit, you have this bell curve, that margin or degree of failure. Our goal today will be to try and minimize or shrink down that bell curve. And again, by comparing things and getting a better understanding of what failures are being caused and at what level those failures are being generated at. HASS is a screening test that is typically applied after the manufacturing process. So HALT is usually done in design and development process. HASS is usually done after manufacturing to verify that there weren't any additional weaknesses or changes to the original HALT product. So when we run HALT tests especially, we are often left with questions regarding failures, repeatability, and validity. there's a whole list of questions here. Some of these I may be able to answer. Some of these I will be able to shed light on. And some of them are still going to be questions at the end of the day. So why does the product fail in one test but not another? And this is one of the target areas of today's presentation. It's comparisons. So different mounting locations, different orientations on the table, completely different HALT machines, all can provide different results. Why does the product fail during step stress but not at full level for the same duration? We'll talk about that one today. How long should the product survive HALT? The product failed on HALT. How would this compare to my end use environment? I have multiple samples. Why don't they all fail at the same time? Is my product being exposed to the desired step stress levels? Simple calibration question. Am I meeting the requirement that I set? What HASS test should I run based on my HALT failures? How many products must be failed to find a statistically representative failure level? Does HALT lead to over-engineering a product? And is HALT exciting all my product's resonances as detected in a sine sweep? So again, some of these we will answer, some of these we will not be able to answer because they are still questions. But in order to get into that, we need to have an understanding of what the mechanics of a HALT machine are. So especially the vibration portion, because that's what we're trying to analyze. That's what the tool set that I'm providing is going to analyze, is going to be the vibration segment of the HALT test. So HALT machines, again, combine a variety of stimuli to generate failures in the product. And the goal is to find failures, to break something. The vibration portion, the vibration excitation, is generated by pneumatic hammers that are placed at varying angles under the table to generate 6 degrees of freedom of vibration. So that means you're getting XYZ, pitch, roll, yaw, ideally. Now, one of the issues that happen on a HALT table is depending on how close you are to a hammer and what angle that hammer is at, the vibration experienced by the product can be significantly different. So this is where the issue comes up, or the question comes up. My product fails in mounting location 1 on my table, but not on 2 or 3 or 4. And this can be because the intensity of the vibration is significantly higher in one point when compared to another. So the table vibration is not perfectly linear. Other things that can cause variation would be the amount of mass on the table and the overall amplitude that you're shaking at. So the mass and shift in amplitude change the characteristics of those hammers that are causing the excitation, shifting the fundamental frequencies that are excited. And what this ends up doing is generating vibration in different frequency ranges based on how much mass is on the table. And as you increase amplitude, the excitation frequencies are shifting higher in frequency as well. And we'll see that through some of the data that I have collected that we look at today. In the end, the key here is the table vibration is not linear across the entire table, nor is it evenly distributed across all mounting points. One of the other kind of notes that I learned in my research is over 40% of HALT failures are generated by vibration fatigue. So the vibration fatigue plays a significant part in generating failures on the table. So understanding and having a better understanding of what is happening to the product and how the product is being excited is critical to improving HALT analysis. So here, we're going to start talking about validation and then some of the comparisons that we can do. The basic Observer 1000 PSD analyzer can be used to generate a GRMS plot, so generate a PSD, calculate the RMS levels. In the newer software that's not released yet, but we have a beta software where math traces will work in the time domain, so you can calculate an RMS time graph so that it will actually show you the RMS versus time. But this could be used to map out different machines. It could be used to map out locations on the machine. You can measure changes to the table response based on changes in mass or table location or orientation. Simple time waveform, time math traces, PSD analysis, and potentially a spectrogram. This would be the simple analysis. It would require a few parts of ObserView, but could be easily done. The more complex analysis is what we are going to look at today. And this is going to utilize all of those other graphs plus the fatigue damage spectrum. The fatigue damage spectrum is, as we will see, a tool that allows us to get a relative damage per frequency bin accumulated over the entirety of the test. And the fatigue damage spectrum is based on time domain data. So we're not using FFTs and averaging data together like we do with the PSD. Rather, we are looking at every peak to valley stress cycle for each individual frequency bin, calculating a damage number based on a material property and Q to accumulate damage in each frequency bin, and then we're drawing the lines in between. This allows for relatively accurate damage assumptions to be made for each individual frequency bin and then to generate a fatigue damage spectrum. And what we can do is calculate these values and then compare them across different step stresses, accumulate them across multiple step stresses, and also compare machine to machine, compare location to location, etc. So as you're running your testing, you could have sensors mounted at each product and be accumulating damage for each product to ensure that your failures are occurring maybe not at the same time, but at the same relative damage levels, thus minimizing that statistical variation in between your samples when you're solely basing them on time. So, what we are going to do is walk through a couple of examples. And my examples, I have a comparison that we're going to do. So we'll walk through creating some graphs, doing these comparisons, utilizing math traces, and then the second application will expand on that to talk about accumulating damage across multiple step stresses and generating a demand comparison or a damage comparison based on duration. And then the final application will be using this tool to generate a demand line that could be used for setting tolerances or achievements for each step stress based in the damage domain rather than in time and RMS. So I'm basically going to skip out of the presentation. I have example slides in the presentation that I could walk through, but it's just duplicating the work that we're going to walk through live anyway. So here is my time waveform, and this is HALT data collected on different machines. So I have different locations in A1 and A2, different machines in A and B, and then different stress levels in 6 GRMS, 12 GRMS, and at the bottom down here I have 20 GRMS. So the first thing that I'm going to do, just to make everything a little bit easier to understand, we're going to change our trace colors here, and I'm just doing this by right-clicking, clicking on trace line options, and then black and red, so that we can more easily differentiate between some of these that we are analyzing. And I'll do this for a few things, and later on it won't matter as much. So to start here, and this is by trace. So there we go. So now you can see, obviously my black levels are much higher than the red. So let's actually just add another graph here. And what I'm going to do is put just the B data from 20 G's RMS. So we'll just look at one RMS level, just B on this graph. And then we'll do the same here, and we'll look at just a 20 G RMS on this graph, so that we can start to make our comparisons. So here I have two different machines. Both locations are included. Things that I can see, I can look at individual distributions here. So if I look at X, you can see I have plus or minus 20-ish G peaks. Y is almost to 50. Z is almost to 40. And then 20, 50, and a little bit wider there. So a little bit of differentiation between location, especially in A1Z and A2Z. But we'll take a look at that a little bit more as well as we progress. And the same thing for the black machine. Again, the peak amplitudes are a bit higher. It also has some extreme peaks that are much, much higher. But there we can see the differences. And if we overlay all of these on top of each other again and start to look at machine A versus machine B, you can see that the relative peak accelerations for A are in that 40 to 50 G peak range. You have a few extremes out beyond. And then, this is in the 60 to 80. So obviously, black is higher in amplitude than red. So now let's add another graph here. So I'm going to click Add Graph, and we're going to add a PSD. Same data set. Again, this is A, so we'll make that red. And I'm actually going to add the B traces as well. So this is again that 20 G RMS data, B, trace line options, black. So there I can again see black is relatively higher than red. Beyond that, the PSD is not incredibly useful. I can do things like add a cursor and use an RMS cursor. So if I go to RMS, I can use the home key to set my base cursor location and then press insert. And now calculate the overall GRMS for this range. And what's interesting here is I have my demand set at 20 GRMS, yet you can see that none of these are even close to 20 GRMS. So that's a calibration issue. I suppose we could look at vector. So if I wanted to do a vector, I could simply add a math trace. And typically vector is square root of the sum of the squares. So what I would do is, I actually have a little cheat sheet over here that tells me what vector numbers each of these are. So if I wanted to do the vector of B2, I could do square root of V the vector number is 34 times V34 plus times square root of the sum of the squares V36 times V36. So now if I hide a bunch of these channels, there, my vector sum is a little bit closer at 18.89 G's RMS. So that is getting close to that 20 G RMS demand line, but that's also picking the highest values out of all of these. A and B, all the rest of the A's and B's are much lower in amplitude, so I don't think that summation is going to work for them. So I can use the RMS cursor to view the overall RMS levels. I can see that overall black is higher than red, but in the end, the values of this PSD are relatively useless. Since the data is averaged over time, I really can't get an understanding of what's happening for the entire duration of the test because the PSD isn't cumulative. It's a snapshot. And that leads into our FDS analysis. So the fatigue damage spectrum, if I scroll down here and calculate the fatigue damage spectrum for this, what this is doing is accumulating damage for the duration of the test and then displaying what that resultant damage is for each one. Now, we have some damage properties down here, our octave spacing, the frequency range that we're analyzing, our M and Q, and those are the values that we're using to calculate the relative damage, assuming there's a resonance at each one of these, what turns into a single degree of freedom oscillator or a very narrow band frequency. So the FDS is accumulated, resulting in a much smoother trace than the PSD. We can also start adding math functions to this to even further simplify our comparison. So if I add a math trace, and the first comparison that I want to do is just the combination of damage, so the sum of A2 versus B2. So same position on the machine, but two different machines. So same relative location, but two different machines. So we will call this one A2 sum, cumulative damage in the 3-axis. So if I pull up my little cheat sheet here, we're doing A2, and I'm actually going to include the 6G RMS and the 12G RMS levels. Well, let's just compare the same. We'll start with a simple one. So A2 is V4, V28 plus V29 plus V30. And I could type in this entire channel name, but each one of these channels is assigned a vector number. As you can see, it automatically populates that. So I can simply type in V28, V29, and V30, and it populates that. If I do type in the wrong one, or if I want to change this formula to calculate different values, by typing in a vector number, I can also quickly switch to a different variable that's assigned to that vector. So there's my A2 sum. I'm going to do a new math trace, and we're going to do B2 sum, B2 underscore sum, and those are V34 plus V35 plus V36. And now if I make this red and a couple lines bigger, make this black and a couple lines bigger, that should clarify things. If we hide those, now we can see the difference between these two particular machines. And if I really wanted to get fancy, I can add another math trace that will tell me relatively how much more damaging one is than the other. So if I do this, my A sum divided by V34 plus V35 plus V36, my B sum and then I can even turn these two off. So I could see at this particular frequency, change my cursor here to a standard cursor. So if I look at this frequency, it's 1E12 times more damaging, and that's red is more damaging than black. But the majority of the time you can see all of this is less than 1, so it's significantly less damaging. And that is reflected in this trace. This gap right here is quite large. But there's a simple comparison of machine A versus machine B. The other thing that we could do is compare locations on the table. So that changes, let's just look at, let's say, the A data and the change that occurs with a change in amplitude or a change in position. So we'll leave all of our A's, we'll turn all the A's on. And then we'll create some new math traces as this is calculating. So I can get rid of these three. Click Add Math Trace. And now we are going to compare, let's do A1 at 6 GRMS, 12 GRMS, and 20 GRMS. So again, I'm going to bring up my cheat sheet. So we are going to look at V1 plus V2 plus V3. That is our A1 6 GRMS combined. And then we are going to look at V13 plus V14 plus V15. This is our A1 12 GRMS. And one more. A1 20 GRMS. And that is V25 plus V26 plus V27. So now, if I look at just these three, what we're looking at here is this shift in overall excitation frequencies, especially in this lower band. Once you get into the high frequency band, especially because we're looking at things as a log-log function, this differentiation gets pretty smeared and stays together because your frequency bins are much closer together. At these low frequencies, though, we can see the difference in the excitation frequencies. So if I make these lines a little bit bigger, I know they can be difficult to see on screen capture at times. So there, this purple line is the excitation frequency of the 6 GRMS level. So it's driving all of its energy into this lower frequency band. And then you can see that each one, as we change the amplitude, so nothing else is changing, the mass is staying the same, the position is staying the same, but as we increase amplitude, that excitation frequency is shifting higher. And that can be a cause of issues in certain tests, especially when you start looking at some of these secondary harmonic bands where that shift is even more visible. So the last example for this kind of application, this comparative application, is maybe comparing cumulative damage of machine A versus machine B. So now what we will do is, well, no, we'll do position A versus position B. That will be interesting. So now we delete that, add a math trace. So this will be our A1 sum. So it'll be the total damage for all of our A1 vectors. And to get that, I need to do V1 plus V2 plus V3 plus V13. So there's our A1 sum, and then we're going to do A2 sum. So this is a different location on the table. So this is A4 plus A5 plus V4 plus V5 plus V6 plus V16 plus V17 plus. All right. So now, if we just look at these two channels, you can see some amount of variation. Overall, the excitation frequency is the same, but as you start to get into these higher frequencies, you do get some deviation where one location on the table is more damaging than a different location. And that could lead to, if you have a resonance that's in this frequency band, it will inherently take longer for that product to fail when mounted in the A1 location than the A2 location. Because you're not getting as much damage at that frequency per, in this case, 100 seconds worth of time. So that is a interesting example. And now we can move on to the next example. So one way to expand on this application is we've accumulated damage across step stresses. So that's what this is. This is the combination of 6 and 12 and 20 GRMS. But now I want to scale that to a projected test duration, whatever it might be, or I want to start comparing damages that might occur, let's say, at 20 GRMS for 3 hours versus 1 hour at 6 GRMS, 1 hour at 12 GRMS, and 1 hour at 20 GRMS. So which of those examples, if I do the sum of 1 hour at 6 GRMS, 1 hour at 12 GRMS, and 1 hour at 20 GRMS, so our 3 levels at 1 hour, versus 3 hours at 20 GRMS. Which of those two examples is more damaging? It's really an interesting question. The answer technically could be both. it depends on the frequency ranges that you are trying to look at. So if let's do edit graph here, and we're going to look at B2. That was the closest to our desired levels. B2 was kind of the best calibrated machine and location. So now what I want to do is compare the difference between all of these summed together set to a 1 hour duration versus just the 20 hours set, the 20 GRMS set together for a 3 hour duration. And in order to extend those environments to a 1 hour duration, we can just add a function to our math, or add a multiplier to our math traces. And that multiplier is essentially the number of passes of our time waveform that we're analyzing that it would take to achieve that desired time duration. So in this example, our waveform is 100 seconds long, and I need 3,600 seconds, 1 hour, so I can just add a 36 multiplier into my math function for 1 hour. So what we're going to do is we're going to look at B2, which is V10 plus V11 plus V12. That's my 6 GRMS, V22 plus V23 plus V24, and V34 plus V35 plus V36. And then we're going to put that in parentheses. And at the end, I'm going to do times 36, because that gets me 3,600 seconds. I have a mistake in here somewhere. Plus, there we go. So this is 1 hour, 6 GRMS plus 12 GRMS plus 20 GRMS. Now I can put in another new math trace, and actually what I'm going to do is just copy this one and then switch to new and paste it in here. Control C, Control V. And I could either change this to 108, or I guess I could put in another parenthesis and do times 3 to get to 3 hours, and then delete my non-20 GRMS levels. Click apply. So this is 3 hours, 20 GRMS only. All right. So now I can hide these. And what we can see here, let's make these a little bit bigger and a little darker to make it easier to see on everyone's screens. So there, what I can see is overall, if I look at the full spectrum, yes, 20 GRMS is in most cases more damaging if you run 20 GRMS for 3 hours than the combination of 6, 12, and 20 GRMS for 1 hour each. But what I can do is set this as a min tolerance. And what that will do, if I change this up here, it will highlight all of the places where, let's set this to there, where blue exceeds, so where my 1 hour at 6 GRMS, 12 GRMS, and 20 GRMS exceeds the 3 hours at 20. And this is just a way to emphasize, or yeah, I can make that even tighter. So I go down to 0.1 hertz definition. That's probably a little tight, 0.5. something like that. So I'm just setting the spacing of these tolerance bands. So right here, there's a spot where blue is higher, but it's, yeah, less than 1 hertz. But what you can see is all of these points. Now, at this low frequency, it's not quite as important, but if you did have a product resonance or some kind of failure that was in these bands, say from 20 to 53, from 71 up to 114 hertz, if you had mechanical failures that were being excited by those frequency ranges, you could see significantly different failure results by running 3 hours at 20 GRMS versus 1 hour at 6, 12, and 20 GRMS. You would get failures that would not occur in one situation. So this is a useful tool for understanding the mechanics of a HALT system and comparing them to each other. All right, so our final example that I want to walk through is just generating a demand line to be achieved during a HALT or HASS test. If I wanted to ensure that I reached this particular line in my testing. And what I'm going to do here, we're going to change this and we're going to call it demand. And that's going to be our desired level. And we're going to change this to, just for the sake of being able to do it in the example that we have, we're going to scale it down to 25% of our cumulative demand. You could be doing this for HALT or HASS testing, where you want to verify that you're achieving 20% of some destruction limit or operating limit. You could build that with this simple math trace. And then I'm going to add another math trace that is essentially the, let's just pick, yeah, I should have left one of those up. The XYZ of B2. That's what we want to do. The sum of B2. I just deleted it. Actually, I did it. So it's still on my clipboard. Perfect. So this is my sum of B2. And what I'm going to do now is minimize this graph. We're going to set this as and a reference. And then I'm going to click play. Oh, missed a step. I did this earlier today too. So I analyzed the whole thing. But right now this math trace, this demand math trace, is shifting based on the amount of data has been calculated. And this could be done using a live analysis tool. So we could stream this data directly while running a test. Or, so now what I want to do is actually make a static copy of this trace and then set that one as my tolerance and this one as my reference. There we go. So now when I click play, we can see our damage is accumulating, And as we get through our test, we could start to see these bins filling in where they're switching to red. Red means that I have achieved that level. Green means I have not achieved my demand line yet. And there I've achieved all of my demand. So that's a great way to validate that a particular set of traces. You could mount accelerometers at each product on the HALT table and set a desired demand line and then run until your product has achieved the desired FDS level for each step stress. That way, the same relative amount of damage is being introduced or induced into each product. This could turn into a bit of a process, but depending on how you have your machine set up and what sample size you have, it will reduce the statistical variance in your failures, because you will be introducing more precisely the same amount of damage or a very similar amount of damage into the product, rather than being subjected to the variation of table mechanics that we observed earlier. So that is the end of my presentation. I hope that this is enlightening, that it at least starts asking questions about ways that we can improve HALT testing. That's really the goal, how to improve and better understand what is happening on the HALT machine and how to better validate the information and the data that we already have. If anyone has any questions, please feel free to reach out to vrsales@vibrationresearch.com or send an email to support@vibrationresearch.com or type in your questions via the GoToWebinar dialogue, and we will answer them as quickly as we can. Again, I want to thank you for your time and look forward to answering any questions that you have. If anyone would like a demo of this software, a demo of the hardware, we're happy to send that out. We're happy to look through your data, to do analysis one-on-one, and to work through any projects that you might have. Thank you, and have a great